Good morning, everyone. So today, up to this point, we know how to, we introduced the concept of the electrical field. We introduced it through the force field. So essentially, through Coulomb's law, for any point charge, we know what the force field of that charge is. We know at any point in space what the force acting on that, any test charge on that point is. But we want to remove the test charge from the equation. So we take the test charge to be 0. And when we do that, we get something, we derive something called the electrical field. It is a force field, but it is the force field on a unit test charge. So it's not Newton. It doesn't have units of Newton. It has units of Newton per Coulomb, right? So we the reason we want to do that is we want to describe the electrical field due to its source, solely due to its source. So for any source, we can describe a force field around it, and that force field per unit charge around it, that force field per unit charge around it is what's called E, which is at every point in space, which is what we call the electrical field intensity, right? But then we said that in electrostatics, a basic fundamental property applies, which is linearity, superposition. So this is a great thing because now we can handle the problem of multiple source charges. What if we had multiple source charges? We can calculate the electric field intensity separately for each source charge, and then sum them up to get the total field intensity. And furthermore, this allows us to deal with charge distributions, because let's say I have a charge on a wire, like an overhead wire, right? I can always divide this into small segments and consider every small segment to be infinitesimal. So every small segment is a point charge. And I can calculate the field for that point charge, and then I can sum over all the segments, which is equivalent to integration when you have a continuous segment like this, continuous region like this, interval like this. And we can do the same thing for surface charge distributions and volume charge distributions. So everything falls down from the Coulomb force law, which allows us to derive the force intensity or the electrical field intensity, which allows us, coupled with superposition, allows us to calculate the field exactly for any distribution, right? Now, the calculation itself is cumbersome. This sort of integration is going to be cumbersome for anything but the simplest and most symmetrical examples. Actually, when we go further in a lecture or two, and we start using something called Gauss's law, which we introduced but only mathematically previously, we'll discover that using something like Gauss's law actually is much simpler than doing this direct integration. So yeah, so this is it in a nutshell. I want to do like a couple of examples to show you how this kind of calculation is going to be carried out. One thing we said is that when we're integrating, always when we're, let's say we have this volume and I'm finding the field E at a point P. P is fixed. Although P is symbolic, it could be any point in space, it is fixed for this calculation. We zone in on a certain point, we fix it, and then we're integrating over the volume. So the volume is varying. So our coordinate varies on the source. And the way we want to, the convention that we're going to use to differentiate between something that we're summing up over space, because we're going to integrate the electric field over space when we do like a line or volume or surface integral of the field itself. But when we do this sort of calculations, we're integrating over the source. When we integrate over the source, we're going to use the prime convention, where we're going to, let's say you were using Cartesian coordinates, X, Y, Z, we're going to add a prime. This prime signifies that we're integrating over the source. Okay. Let's do an example of a line. Let's say I have a straight line. And the problem is, let's say take a point A, distance A from the line. And this is a charge line. This has some rho L on it, rho L coulomb per meter. Let's say this is a uniform charge distribution, right? Then rho L times the length of the line is going to give me the total charge of the line. But the idea, what is the field, right? So here, when you encounter this problem, first thing you want to do, you want to introduce a coordinate system, right? It would be stupid to introduce a coordinate system and then have the line here. Why? Right? That's stupid, because a coordinate system is your choice, right? So you can always introduce the coordinate system to simplify your life and make use of the symmetry of the problem. So I can always rotate this, right? I can always rotate this like this. So this is the line segment. And I can always place my coordinate system, origin of my coordinate system, at the center of the segment, right? So let's say I want to go with cylindrical, right? The line has cylindrical symmetry. Look at it from any direction, it's a line segment, right? So I'm going to have small r, and then I'm going to have z coordinate. Imagine z is on the line. Let me draw it better, I guess. So this z coordinate. And then phi, of course, is in this direction. Right? But it doesn't matter. The field at a distance a, so the point A is here, actually. The point where we're finding the field is here, right? And this is the distance A. So we use the symmetry of the problem. Does it matter where A is situated? Right? Let's say I have this line. Does it matter if A is here, or A is here, or A is in the back? Right? So imagine line segment, A is here, 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 here. Doesn't matter, because you can always rotate. It's a completely symmetrical problem. The field will be the same. It does not, what I'm trying to say is that the field is only going to be a function of R. It's not going to be, and Z. It is not going to be a function of phi. Doesn't matter what angle you are. And we're simplifying our problem. We don't care about Z again, because we imagined our coordinate system to be in the center. So our problem says, find the field at the center of the line segment. If the problem was find the field here, at the end, it will be more difficult problem. But we're considering the symmetrical problem, which is just find the field at the center. What is the field at the center? And we're going to try to do the calculation using using no assumptions, meaning the line segment length is L. And then the second question we'll try to answer is, what happens if A is really small? Meaning, what happens if we close to the line segment? Like similar to an overhead line, when the line is, you can consider the line to be most likely infinite. As far as you're concerned, the line is infinite because it just keeps going both directions. So what would the equation for the field be if we assume that the length of the line is infinite? L goes to infinity, which is a reasonable approximation in many practical problems, like an overhead line, right? Your distance from the line is much, much less than the total length of the line. Right? The line could be coming from Raleigh into Charlotte, right? And you're standing above it. So when you calculate the field, you don't need to consider, you might as well consider the line to be infinite. Okay. So when we look at this problem, we need to divide the line into segments. So let me take this segment here, small linear segment. And this linear segment has a length of dz prime. Now, again, I'm using the prime convention because this is a source. I'm integrating over the source. Now, this is going to give me a field at point P that points in this direction, infinitesimal field, dE. The thing is, there's a symmetry, special symmetry of this problem such that, so this is at a certain z prime, let's say equals, I don't know, B. At a mirror point where z prime equals minus B, this is also going to give me a field DE. And notice I can decompose this field into I can decompose this field into, let me use another color, into a parallel component to the R-axis and a normal component. And notice that the normal components cancel out. So wherever we take this, no matter where we go in DZ prime, let's say we go from 0 to the length of the wire, there's always be length over 2, right? Because I'm centering, right? There's always be an opposite point here that's gonna cancel the tangential component of the field. Really, the field at the center will only have, sorry, the norm component of the field. The field at the center will only have a tangential component. And this tangential component is gonna be DE, the total field, cosine alpha. Alpha is this angle. Okay. So when I find the DE is what is the charge? What is the charge of this differential element? It's going to be rho L. Let me go back to black. Rho L dz prime. I'm going to leave a space over 4 pi epsilon. This is Coulomb's law. What is the distance here? What is this distance? This is like a right-sided triangle, right? So this is going to be z prime here, the z-axis. This is going to be a. Right? So this distance is going to be square root a squared plus z prime squared, right? But this is going to be r squared here. This is r squared. So r squared is going to be a squared plus z prime squared. Right? Now, this is not what we are. This is the whole field, right? But we want to use the symmetry and we want to consider only the tangential element. So the tangential element, we get it by multiplying by cosine alpha. And then we have to integrate this, right? From minus z prime equals minus 1 to z prime equals 1, right? So because now when we are at here, the opposite element is going to cancel the normal component, and we'll get only the, wherever we are, the only thing contributing to the integral is the tangential element. The rest, the normal elements, get canceled out from the symmetry. So this simplifies matters a great deal. So this is Coulomb's law, rho L cosine alpha dz over this, and then we integrate it over the whole line segment. And this is what this is in the r hat direction. So yeah, from Coulomb's law and the symmetry of the problem, we reduced the problem of finding the electrical field to finding this integral, Newton over Coulomb. How do you find this? I mean, I could say cosine alpha from this graph. Cosine alpha is the it's a triangle. So the side of the triangle is A. So this is A over the hypotenuse, which is a squared plus z prime square root. That's what cosine alpha is. So I can rewrite this as r prime. Z prime is from -1 to 1. Rho L is going to have a dz prime over a squared plus z prime squared times square root is going to be 3 over 2, power 3 over 2. And now this is just a matter of going to an integration table and finding this integral. So what's the indefinite integral of a over a squared plus z prime squared 3 over 2? This is the sort of problem. Well, it turns out to be, well, it turns out to be z prime over square root a squared plus z prime squared. You can check that. Like if I take d over dz prime of this, I should get this. And we can check that. I mean, it's going to be the denominator times the differentiation of the numerator time minus the numerator. You know how to do a quotient derivative, right? times the differentiation of the denominator, which is over 2 a squared plus z prime squared over the denominator squared, which is a squared plus z prime squared. Let me see, is this correct? Oh, there's a 2z here. So I differentiated the square root. So 1 over 2 square root a squared plus z squared, but now I need to differentiate what's inside the square root. It's the composition rule. So there's a z prime squared. So this is going to be an extra 2, an extra z prime. So it becomes 2z prime squared. 2 cancels with 2. Okay. And then I can multiply both sides by a squared plus z prime. I can multiply numerator and denominator by square root a squared plus z prime squared. So I end up with a squared plus z prime squared minus z prime squared. This cancels with this over a squared plus z prime squared 3 over 2. Right? So we're almost there. What we need to do is we need to have an a squared here. Okay. And then I have 1 here. So I'm just taking a out. So this is clearly, when I differentiate this, I get this. Right? So I know how to now write my integral. So E, the indefinite integral is going to be, of course, rho L is constant, A is constant. And then this is going to be z prime over, let me write it this way. It's going to be z prime over a squared square root a squared plus z prime squared. And this is evaluated from -1 to 1. I could take, I guess, the a squared out, end up with rho naught over a. And then I forgot something. I forgot the, oh, 4 pi epsilon naught. That's what I forgot. 4 pi epsilon naught. So I end up with rho naught over 4 pi epsilon naught a. And then I just plug in 1. No, there's no 2 here. Plug in 1. So it's going to be 1 over a. 1 over square root a squared plus 1, right? Minus 1 plus 1 over square root a squared plus 1, right? This becomes 2, so we end up with E. I can take the 2 out, so I end up with E being rho L, this is rho L, by the way, over 2 pi epsilon naught A square root 1 plus a squared. This would be the electrical field. If I have a rod and I take the center of the rod and I take a distance a from the rod, and I want to find the field at that point, this is the exact equation for that. Any place other than the center of the rod becomes much more difficult, because we lose the symmetry. And that's the nature of many problems in this subject. Many problems in the subjects can really be only solved numerically. The examples that can be solved exactly analytically are few and between. You know, they're like textbook examples, academic examples. Most of in the real life, most of such problems, if you want to solve them really, you have to end up solving them numerically. Okay, but this is one of the few things that we can solve exactly analytically. What happens if we take now what happens now if we take the distance to the length of the rod to be infinity? Well, the limits of the integral are going to go, instead of 0 and -1 and 1, they're going to go from minus infinity to infinity. That's the difference, right? So the field is going to be the same, except here my limits are going to be infinity and minus infinity. Okay. Can I find what that's going to be? Yeah, that's easy. So this is going to be z prime is infinite, right? Because z prime is infinite, this is going to be z prime over z prime infinite squared, infinity squared, a squared. That's going to always equal z prime squared, right? So I can, a squared is much smaller than z prime, right? So I can take the limit is reaching infinity. So I can ignore a, and I end up square root of z prime squared, which is z prime. So it's going to be z prime over z prime. So it's going to be 1. Okay, minus infinity. So it's going to be minus z prime. Again, minus infinity squared is infinity. So it's going to be z prime. So it's going to be minus 1. So minus 1 is going to be plus 1. So this is just going to be 2. This whole thing is going to just give me 2. If I let the limits go to minus infinity and infinity due to the limiting process. So if the length of the rod approaches infinity, meaning length of the rod is much larger than A, that's another way of saying it, then E is going to be, this integration is just going to give me 2. So E is going to be rho L over 2 pi epsilon naught. A. And that's it, Newton per coulomb. Okay, you want to check that, is this right or wrong, by the way? One way you can check is by checking the units, right? Because from everything, you know, the electric field comes from something like Coulomb's law. And Coulomb's law expects a charge over something with epsilon naught over a distance squared. Here, I don't have a distance squared, I have only distance, right? So that means this charge is Coulomb per meter. So there should be an extra place where the meter squared comes from, and it comes from here. So this meter comes into this meter coming from A here and gives me meter squared. So the units make sense. I have Coulomb in the numerator. I have permittivity epsilon with its units, and I have, although I have 1A, the extra meter coming from the density joins that A and gives me the meter squared. So the units make sense. This, in terms of units, this equation makes sense. So now you know, anyone gives you a rod with a uniform charge density. Oh, one other simplification here that you have to consider is I took rho out of the integral. I'm assuming a uniform charge density. If the charge density was not uniform, it would have been a different problem. It would have been a bit more complicated expression, if we could have solved it at all. And for some example problems, we could solve some symmetrical charge distributions. But here the assumption is a uniform charge distribution. But now you know, like if you have a rod and you have a charge distributed over the rod, you can find the electrical field from the center of the rod, at any distance from the center of the rod, and it's always going to be tangential. Okay. So let's do another example. What if I have a hoop, a semi-hoop? So a hoop that's cut in half. So let's say I have something like this, semicircle, and then I'm trying to find the field at the center. Right? So I have rho L here. Okay? So here, the good coordinate system that we can use is again a cylindrical coordinate system, but we're looking at it from above. So this is going to be this has a certain radius A. So the radius is fixed. Okay. So yeah, so we can take a small segment. So let's say we wanna use the symmetry of the problem. So we're taking phi. So phi is going from 0. So this is, let's say, the coordinate phi. So this is blah blah dot dot, and this is the coordinate phi. This is what we're integrating over. We're varying phi. Here I'm going to use phi prime because I'm varying it over a source. So the segment, the line segment here is going to be dl prime, and we know for a cylindrical system, this is going to be the r d phi prime. R in this case is a d phi prime. This is the linear segment. Okay, and then we know from symmetry that this is going to give me this sort of field, right? dE. But then we know from symmetry that each line segment here is going to have a symmetrical segment here that's going to give me a field in this direction. That's going to cancel. This is going to cancel the tangential component, and we're going to end up only with a normal component. So in this example, only the normal component is going to exist. Right? Only E normal is going to exist. Right? So we can always ignore the tangential component. So in this case, E, the total field, again, we have to apply Coulomb's law, right? So here, the distance, what is this angle, by the way? This angle is equal to this angle, and this angle is just going to be phi prime minus 90 degrees. Right? That's what this angle is. This is phi prime, and this angle is just phi prime minus 90 degrees, and this angle is equal to this angle from geometry. Okay, so E is going to be Coulomb's law, rho L, A, d phi. This gives me the line charge density times the line segment, gives me the charge over 4 pi epsilon naught. And now we have to determine this distance. What is this distance? A, right? This distance, it's a semicircle. So distance is always going to be radius. It's going to be A squared. And that's it. That's what we're integrating over. So we have to integrate this from 0 to 2 pi. Sorry, from 0 to well, we could do from 0 to pi. We could do from 0 to pi, but there's a certain symmetry of the problem, right? If I integrate from 0 to pi over 2 and just multiply by 2, I'll get the same thing because the problem is symmetrical. Integrating from 0 to pi over 2 is going to give me the same result as integrating from pi over 2 to pi. I can just do this. I mean, so that's fine. So this kind of simplifies, and I end up with 2, and then 0, and then I end up with oh, I'm not done yet. Actually, I'm not done yet. I'm not done yet, and the reason I'm not done is because I want to ignore. I'm trying to ignore the tangential component. So this is going to be this is 2. This is A for 4 pi epsilon naught A squared. So this cancels with this. I end up with A. But I want to ignore the tangential component. So the tangential component, I want to ignore the normal component. I'll only consider the tangential component. The tangential component is always going to be the field, this field that I'm calculating, projecting it on the normal. What is the angle of projection? It's this. So it's going to be, I need to multiply this by cosine phi prime minus 90 degrees. What is cosine phi prime minus 90 degrees? I use the identity, trigonometric identity. This is going to be cosine phi cosine 90 degrees, which is what, 0. Right? I believe then this is going to be plus sine phi, sine 90 degrees, which is 1. So this is really going to be sine phi. Sine phi prime. Okay. So this becomes simple. This problem reduces to 1 over 2 pi rho L. over 2 pi epsilon naught A, and I'm integrating sine phi prime from 0 to pi over 2. Right, so what is this? This is this constant, and this is cosine phi prime minus cosine phi prime, 0 pi over 2. Cosine pi over 2 is 0, minus cosine 0 is 1. This whole thing goes to 1. So the electrical field turns out to be rho L over 2 pi epsilon naught A. Is this similar to what we got here? Interestingly, it's similar, right? So interestingly, it's similar. So we get the same sort of electrical field. Right, so rho L 2 pi epsilon naught A, rho L 2 pi epsilon naught A. So the problem of finding, if you have an infinite line, problem of finding the field at distance A from that infinite line with charge density rho L, right, is exactly the same field if we have if we take this line and we chop it off and we do a semicircle with radius A. This gives me exactly the same field, which is an interesting result. Because here, although we have an infinite amount of charge, because the line is infinite, the charges are moving farther and farther away. So they're not contributing. But here we make them, we make the number of charges finite, but we bring them closer, right? So this is equivalent to this. Okay. Okay, what I want to say, I think I had another point, but yeah, that's fine. All right, so surface, example of a surface charge distribution. What if you have a sheet and someone tells you with a charge distribution rho S, someone asks you, what's the field at any point at the center? So this is the center of this sheet. And no matter like a small distance, let's say a small distance, or whatever the distance is, what is the field there? Sorry, I guess the problem, no, this is different. What is the field at the center of this sheet? Right? Instantly, you should say it's 0, just from symmetry, without doing any calculation, because I can look upwards, and this is point P. I know that I have to integrate over the surface, but I know that for any surface element ds, that's going to give me this field, dE. I'm going to have symmetry of those surface elements, right? So this is going to give me this field, but then I have the mirror image of it that's going to give me this field. And then I have this that's going to give me this field. And then I have the mirror image of it that's going to give me this field. And it's all going to be equal and cancel each other out. So if you do the integration over the whole surface, the field at the center of this sheet should be 0. You don't even have to do the calculation. Okay. What about a hemisphere? What, like a sphere like this, like hemisphere. You take a sphere and you cut it in half, and this hemisphere had a radius r. What is the field at the center of the hemisphere? Okay. So this I can use cylindrical, cylindrical or spherical. Yeah, cylindrical is better actually. No. Spherical is better because the surface itself we're integrating over has spherical symmetry. So I can shop this. I can look at it from the Z. I guess let's do cylindrical. Okay, let's do spherical. I'm just putting Z. I'm putting Z here, but I'm not using that. I'm just, for orientation with respect to the XYZ coordinates. Z is there. And then I'm looking at sideways on a cut. I'm cutting, I'm slicing the hemisphere. I'm looking at it from the side. And then this is distance R. And then in spherical coordinates, I have coordinate theta. This is coordinate theta prime. Remember, prime, because I'm integrating over the source. And then here I have a volume element. So surface element. Although I'm drawing it as a segment, it's this surface, right? So ultimately, we have to integrate. We have first to integrate over this line, and then we integrate over phi prime, so that we kind of like cover the whole sphere. So this has this is ds prime, and this the surface charge density is rho s. And then again from symmetry, the field is always going to be normal. This is going to be in the z direction, dez, right? Because if I have field coming from here, I'll have its opposite element here giving me a field going in this. So this element gives me a field going in this direction. Then this element gives me a field going in this direction. The tangential elements cancel out, and we end up only with the normal element. And as you traverse the sphere, the traverse row, the same thing happens. Everything cancels out except the normal element. So what is DE in this case? DE is going to be let's see. D is, according to Coulomb's law, is going to be R prime let me actually only write this element. This is what I'm calculating, right? So so what is the field due to what is this volume element? This volume element is first, this is phi prime, right? Okay. Let me see. Okay. The surface element is going to be sine phi prime d theta prime d phi prime r squared. Remember, right? Let me double check if that's correct. Yeah, it is. It had an. If I go back to the. Oh, we have it. Coordinate system transformations. If I go back to the surface element for spherical coordinates, in the r direction, it's r squared. So this is the surface element, right? This is in if you go back to the notes on the surface element for in spherical coordinates, this is it, r squared sine prime phi d phi prime d, right? But then I multiply this by rho s, and then Ohm's law, Coulomb's law says 4 pi epsilon naught r squared. Okay, so this cancels with this. Okay. So that's why I don't have r squared in the denominator, because it cancels with the r squared of the surface element. But then I said I only care about the normal component. So I'm going to forget about the tangential component. So I get the normal component from the total field by projecting this into the normal axis. So I have to multiply by cosine phi prime, theta prime, sorry, d theta prime. And then we have to find the total field. We have to integrate this, this is a hemisphere. So we have to integrate. So I have, let me put d phi prime, d theta prime. I'm integrating d phi from 0 to 2 pi. Phi goes from 0 to 2 pi to get you the whole sphere. So phi starts here and goes to 0 to 2 pi to cover the whole sphere. And then theta goes from 0 to pi over 2. Right? Theta goes from 0 to pi over 2. Sine theta prime, cosine theta prime. And that's it. This is the integration that we have to find. Do we know how to integrate sine theta, cosine theta, d theta? Yeah, we know how to do that. This is easy, right? Because if yeah, so you can look up any table. This is going to be just minus cosine 2 theta prime over 2, right? You can differentiate this and see what you get. So this is going to be, is this true? Let's differentiate this. So let me differentiate this. So this is going to be, I mean, how would you do this? So this is going to be, let's assume you can do substitution. So assume u equals sine theta prime. Du over d theta prime is just going to be cosine theta prime, right? So I can take d theta prime here, just doing substitution. So cosine theta prime, d theta prime is just du, and this is u. So it's going to be integral u du. So it's going to be half u squared, right? That's what's going to be. So the integral is going to be half sine squared theta prime. Okay. But then I don't want to deal with squared, so I can use the identity. You know, from trigonometry, you have cosine 2 theta prime equals cosine squared theta prime. You can write this. You can write this as in terms of cosine, right? So this is going to be. So what's cosine theta prime plus theta prime? That's going to be cosine squared theta prime minus sine squared theta prime, and then cosine theta prime minus theta prime is going to be cosine squared theta prime plus sine squared theta prime. Is that let me see. I'm trying. I forgot the trigonometry. But anyway, I mean, easy is going to be. Oh, what happened? Oh, the thing is, d phi. There's no d phi here, right? So this is going to be 2 pi. So it's going to cancel the pi and the 4. So it's going to be rho s over 2 epsilon naught. And then I'll end up with the integral of this. So this is going to be, I don't have to simplify this. This is going to be half sine square theta prime from 0 to 2 pi. What's sine? Oh, pi over 2, sorry. So the half goes out, and it's going to be 4. Yeah, I don't know why I was trying to simplify this further. I think this is simple enough. So sine squared pi over 2 is 1. Sine 0 is 0, so it's going to be 1. This whole thing is going to be 1. So the electrical field in the tangent, in the normal direction, is going to be just rho s over 4 epsilon naught. I can add in the basis vector for cylindrical coordinates or Cartesian coordinates, doesn't matter, which is the minus z hat. But notice this is interesting now because the units need to be fine, right? So this is a surface charge density. So this has Coulomb over meter squared. So the meter squared is already there. So it makes sense because the meter squared is already there. We only need to have epsilon in the denominator. We don't need to have something that's gonna add, right? You know, the inverse square root according to the square law, according to the units, still makes sense, right? Previously, one of the meters went into the line charge density. So we end up with one variable representing distance in the denominator. Now that we have a surface charge density, both meters in the meter squared in the denominator goes into the charge density. And we don't have to worry about anything. It naturally arises just from units, right? This is E. The force on a unit charge, of course, is going to be force. It's just going to be minus Q rho S over 4 pi epsilon. This is the force. The last example we want to do is a volume charge density. I don't know if we have time to do it. But essentially, it's a volume charge density of a cloud. What would be the electrical field under the cloud? Let's say you're standing under a cloud, right? So when this kind of like we apply. There's a famous joke where if you want to do a calculation with a cow, just assume a spherical cow. So this is one of those things where we just assume a cylindrical cloud. We assume the cloud to be a cylinder, and then we're centered at the origin, and then a distance h underneath the cloud, from the middle of the cloud, right? We want to find the field. I think I'm gonna do this example quickly next time. It should be a simple example, and then we're gonna move on. Any questions so far? All right, everyone. Ciao. See you Wednesday.